We're going to talk right now about water potential. So, water potential is a mathematical calculation, and it is how we determine where the water is moving in a cell. Is it moving into the cell? Is it moving out of the cell? Just like we talked about during the membrane potential notes, but this one really has to do with the math behind how it's moving. So, couple words that you should be very familiar with right now are going to be hypotonic, isotonic, and hypertonic, as well as the words on the bottom turgid, flaccid, and plasmolyzed. If you take a peek at all of these, you should be able to find the one that is the appropriate set of conditions for the animal cell and the appropriate set of conditions for the plant cell. You hopefully decided in the brief moment I just gave you there that the isotonic solution is the normal or preferred way that animal cells are, as well as turgid is the preference for a plant cell. So it's always either hypo or isotonic. If you ever think, ooh, the answer might be hypertonic as the preference, no, it's not. It's never any cell's preference to be in a hypertonic state. Water potential, by definition, is just the tendency of water to leave one place in favor of another. So it's really just a measure of the tendency of water to move. Remember that water always follows the concentration gradient. It always moves via regular diffusion. So we are going from high concentration to low concentration, and we don't need any amount of energy in order to do that. There are two major factors in this particular situation, in this scenario, and that is going to be the pressure that is around the given cell, and it is going to be the amount of solute, so all the little particles that are present. Particles on the inside, particles on the outside. This is also going to be pressure on the outside, pressure on the inside. All cells are affected by this, so animal and plant cells are both impacted on this guy. We will talk at the very end a very specific plant cell mode. We'll talk animals during. So I like this picture because it just visualizes every single one of these words. If you can put a picture in your head, you are much more likely to remember something. So if you have high water potential, there's a lot of water that is in that given area. If you have low water potential, then there is not very much water that is in there, and the water is going to be moving towards you. Okay, you can read all the words that are on this slide. If you need a little more help, I'll give you some video resources at the end. Two more microscopic parts that make up the overall concept of water potential are pressure potential and osmotic potential. So pressure potential is just the pressure that the general atmosphere is exerting. So this is just like what's happening in the whole world of the Earth. What's the pressure that's being put on any given cell at any given moment? The osmotic potential is going to be a measure of how much water there is. What's the potential of the water in that given situation? And this is going to depend on how much solute concentration there is. Remember that a solute is the stuff. It's all the little particles that are in any given area. Let's go back to the concept of molarity. So molarity, the number of moles, so how many 6.02 times 10 to the 23rds number of atoms there are. Remember, that's what a mole is. So how many of those are there in the area would be your molarity. How much solute is present? How much stuff is there? Osmotic potential is basically the opposite of that. If it's not stuff, if it's not moles of something, it's probably water. So molarity is going to be a positive number because it's all of the stuff that is in a particular area. Osmotic potential is always going to be a negative number because the two things need to balance one another. So the water is the negative thing. Okay, so as molarity increases, as we have more stuff, you're going to have less water, and then vice versa. There's more water, there's probably going to be less stuff in that situation. Giving that context for you here a little bit is we have the turgor pressure. So if you go back to this one and you're like, wait a minute, why doesn't a plant cell just want isotonic, like even in, even out on this? Here's why. Because in a situation for a plant, and we'll start over here in case A, if you have high water potential, high pressure potential, and high osmotic potential on the outside of a cell, not on the inside, it's on the outside, what that means is the cell, like inside of the cell, probably is low in the water potential, it's low in the pressure potential, and it's low in the osmotic potential. It has not got a lot of water. It does not, that water is unable to exert pressure on the front in the vacuole. Remember, water in a plant is stored in the vacuole. The vacuole is not putting any sort of pressure onto the cytoplasm. The cytoplasm is in turn not putting any pressure onto the cell membrane, and then that cell membrane is not exerting any pressure on the cell wall. So what a plant will look like in this case is wilted. That's what's happening in case A here. If you then water that plant, because the outside is where the water will be, that water is going to go inside of the cell. Shoop, shoop. Now we're over here in situation B, and you are going to have increased levels of potential on the inside of the cell. So now that central vacuole is nice and full of water. We've got a lot of pressure on the cytoplasm. You've got a whole lot of pressure going onto the cell membrane and then eventually onto the cell wall. So what happens is that cell becomes turgid. Turgid is when a plant is in a hypotonic state. So the plant cell is in a hypotonic state, and there is pressure on the inside of the plant that is fulfilling that plant's needs and keeping it perky. So that's why a plant wants to be in a hypotonic state. It's also what turgor pressure is, or being turgid. Okay. If at this point osmosis and water potential are still like, I'm sorry, what now, Miss Bao? I don't understand. Please hit the pause button right now and please go watch this video. You can just Google it real quick, or if you would like, you can go and you can open the slide deck, scroll down to this slide, and then you can watch in there. It'll just show up right away. Either one is fine. Whatever it is that you need on this guy, I just want you to go take a peek if you need more. Nope, we're not watching it. All right, the mathematical formula, the calculations. If that little letter that is on the screen at the top is not familiar to you, it's about to be. It is the Greek letter psi, P-S-I, or sometimes we call it trident. The water potential is the first one. That's that big bar in the beginning. So trident, or water potential, is going to be the sum of all of the solute potential and all of the water, the pressure potential that is there. So what's the pressure that's happening in there, and then how much stuff is present in that given area. The unit for pressure can come in 3 different ways. It can either be listed as bars, it can be listed as atmospheres, or it could be megapascals. All 3 are appropriate ways. They all work. Doesn't matter. Just pay attention to whatever the situation and whatever the scenario is giving you. It'll be one of those 3 things. Most of the time, it's going to be bars, but it could be something else. Pure water, so H2O, open container, sitting out just on the counter, you are going to be at a 0. The pressure potential in that situation, or the water potential in that specific situation would be 0. So if you ever need that value, if you ever need that number, and it says something about like, this is pure water and the container is open to the air, and you're like, what in the heck is the the water potential then? 0. No potential. No movement, no nothing. Nothing is happening, nothing exciting, nothing. Sometimes we like to use these 2 words interchangeably. I wish that we didn't, but it just is the way that it is. Sometimes we can mix up solute potential and then osmotic potential. So sometimes we use those words interchangeably because we are literally just talking about how much solute is in the area. And if we know how much solute is in the area, then we would know how much water or osmotic potential there is. That's like the movement of water across that membrane somewhere. So if water is moving out of the cell, and you are in some sort of a hypertonic or plasmolysed state, you have a negative pressure potential. So if you can get a negative pressure potential, that means water is likely on the exiting movement. And then the opposite of that, if you have a positive pressure potential, so like the water has all moved in and now we have nice fluffy cells, you are likely in a hypotonic sort of a situation. Remember, hypotonic, good for plants, bad for people. The second number mathematical formula that you are going to need to do is the calculation of the solute potential. So solute potential is calculated in this way. It is negative ICRT. And here's what all the letters stand for. Remember, it's always negative. This is how it's always negative, because it's just literally negative right there. The I is known as the ionization constant. That is how many ions or particles will the solute break apart into in a given situation. Typically, this is going to be, think about your periodic table, or use one in the classroom, something from the left side of the periodic table and something from the right side of the periodic table. If they are stuck together, they, in a container of water, will break apart. You know this, sodium chloride in a beaker of water stops being sodium chloride. You get sodium ions and you get chloride ions. Whatever breaks apart in there, if you have two things, and they can do this thing called dissociate, so they can split apart, that counts as two ions. So you would have an ionization constant of 2 in the case of NaCl, sodium chloride. In the case of this bottom one, we have Ca, that's calcium, Cl2. So calcium is on the left side of the periodic table. Chlorine is on the left side of the periodic table, calcium is on the right. If we put those two together, 1, 2 chlorides, oh, look, we have 1, 2, 3. So then we end up with 3 ions that are in there. If your stuff is all from the same area on the periodic table, as is the case with all of your sugars or carbohydrates, then everything is going to be what we know as covalently bonded. So that's a way that the molecule is sticking, the elements are sticking together, and they will never break apart from each other. Only things when they come from the left and the right side of the periodic table break apart from each other. If they're all on the one side, then they're going to covalently bond together, and they never, ever, 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 ever break up. So then we say that their ionization constant is 1, because it's all one big giant molecule. R is just a constant. That value, that letter, that number, that 0.0831, that's that number always and forever. Unless they give you it differently, that's the number that you need. You don't need to memorize that. I will always give it to you. The unit for that is bars per mole per Kelvin, or bars per mole Kelvin. You do not sub in a mole. You do not sub in a Kelvin temperature for those two places. That's just literally the unit. The reason that you do that is so that when everything lines up, all of your units cancel and you're left in the unit that you want, the various given unit, whatever it is that you're looking for. Okay? None of those are things to sub in. Those are literally, that's the unit, bars per mole Kelvin. C is going to be your concentration. It should be a number that's given to you. It might not be. You might have to read a graph to figure out the concentration, but it's something you should just be able to read. And then last but not least is going to be your temperature. Temperature is always in Kelvin in this point. So to get Kelvin, you're going to take your Celsius and you're going to add 273 to it. If somebody was being truly cruel and mean, and that person will never be me, they will give you the Fahrenheit. You then need to convert from Fahrenheit to Celsius and then add 273 to it. I will always give you 273. A good number to memorize or keep in your brain is 22 degrees Celsius is what we say is room temperature. So if you were ever told room temperature 22, and then you do 22 plus 273 to get the Kelvin. If you need a little more and you're like, I want to watch someone do a practice problem, or just like explain it to me again, use this video. There are a ton of videos out there. I have combed and looked through all of them when I was trying to teach myself and when I was trying to find a great sub video for you, like one in case you needed more explanation or you just wanted to hear it differently. This is the one that I like the best. There's tons and tons and tons of them out there. You're welcome to use any of those. I don't always love the accents. I don't always love the video quality. I don't always love the sound quality. I think this one does a really nice job at getting everything in there for you. So if you need it to hear it again, if you want to see a problem done out, this would be the one that I would recommend. For my plant nerds, or if you just have a curiosity about plants, and plants are super fun, I think they're amazing, this is going to be the next thing. So this is a root. The yellow cells that are on the very outside. Don't worry about the blue. Don't worry about the middle stuff. Don't worry about the green. Worry about just the yellow. That's called a root hair cell. And they literally do look like that. They are root hairs and they go all the way out. Through osmosis, a plant is able to suck in water from the soil. You know this. Adhesion and cohesion is how that water gets all the way up to the very top. If you have forgotten, plant respiration or plant movement of water is called transpiration. That's evaporation out of a plant, the water out of it. How that works, yes, adhesion, cohesion for sure is 100% a thing that you should have learned in our very first unit, properties of water, in biochemistry. We did all that stuff. It's because in the leaves of plants, be they needles or leaves, there are these little tiny holes. Those little tiny holes are called guard cells, and guard cells work on a pressure potential difference. If the pressure potential between the roots and the stem, up the stem to the leaves is perfect, then those little guys stay closed and the plant just gets to be a plant. It just does normal things. If the potential drops and it falls, that will initiate the plant to open the guard cells, and now there is a pressure difference between the top of the plant and the bottom, and osmosis, water potential, will start to pull water into the roots, and adhesion, cohesion have it go all the way up to the top and out the leaves. So if you've ever wondered, yeah, but like really how does a plant get water? Yes, adhesion, cohesion, totally super important, but it's also a pressure potential difference for these guard cells. If you have any questions, if you have any concerns, if you have any comments, if you need any assistance with anything, please come see me and I would be happy to help you with anything that has to do with water potential. There's also a formative. Feel free to go try your hand at that, answering a couple questions on water potential and how all of those pieces work.